Please welcome the founder of DataKind, Jake Porway.
Will y'all just do me a quick favor and just stand up in your seats real quick? I guarantee these are not designed for our health. Just give a little shake. I was feeling it. I know how good this feels being up here. But you want that too. Know that you need this because we saved the most exciting topic for the end of the day, data, right? Yeah, woo! So you can all have a seat, and I'll say that we've been talking a lot today about quantifying design. But I actually wanted to take a slightly different tack and ask a question about designing data-driven systems for impact. I, as a statistician in a room full of designers, don't actually come here with answers today, but instead with an appeal for your help. So let's just set the stage on what I'm talking about. We live in pretty insane times. Over the past 10 years, a lot has changed. There are now more cell phones on the planet than there are people. Almost everything we do online is digitized and tracked. We're instrumenting our bodies to measure everything from our heartbeats to what tugs at our heartstrings. And we are instrumenting our globe with sensors across land, air, and sea. And what all of these developments mean is that we now have huge new sources of data, digital information about almost every human activity rushing in that has all sorts of new potential for understanding more about our world and about our communities than ever before. And this is very exciting because in today's conversation, this means we may have new avenues to measure what we're doing in ways we couldn't before. But my hypothesis is that the data is actually a bit of a red herring. Because what this is actually giving rise to is a world of intelligent machines. That's right, algorithms that are making decisions around how we live our lives, whether that's Netflix deciding what we want to watch, or Google and Uber finding the fastest route between point A and point B, Amazon deciding what you want to buy. Yeah, this is mine, no shame. It's true, the way it works. Or even beating us at some of our best human domains. Google's DeepMind recently defeated the Go champion, long thought to be a game that computers could never compete in. And so we're suddenly at this age when we talk about data, not just in terms of thinking about evaluation looking in the past, but actually as a resource and a medium for these smart machines to suddenly start spinning up and doing really incredible, quote-unquote, intelligent things. And looking at this landscape, I'm reminded of this poem from the 60s by Richard Brodigan I love, called All Watched Over by Machines of Loving Grace. And if you haven't read it before, it's only going to be up for a second, so I'm going to read the last stanza, which says, I like to think it has to be of a cybernetic ecology where we are free of our labors and joined back to nature, returned to our mammal brothers and sisters, and all watched over by machines of loving grace. And whether you find that utopian or dystopian, I really think Richard was earnest here and said, well, how could we create this world in which these smart machines live alongside us and deliver us our health, and maybe we don't have to work anymore? It was a beautiful utopian vision, but one that we're pretty far from when you think about what we've used this tech for so far, buying Snuggies and watching movies. So we've been thinking about how would we design intelligent systems so that we could achieve this vision, one in which we have a healthy climate and where people are living alongside machines in harmony. And so we think about that a lot at our organization, DataKind. We're a nonprofit that seeks to use data science towards social and humanitarian causes. And our little piece of this puzzle is that we try to bring together data scientists from the tech sector who want to volunteer alongside social organizations so that together they can use data to build designs or design systems that help them improve their impact. So I'll show you just a few quick examples of where we see algorithms and data science actually helping out in this endeavor. So the first comes from a group called Crisis Text Line. It's a fantastic program that helps teens in need, where they can text and immediately get help from a counselor when they're in crisis. You know, teens don't call anymore, they text. So it's a pretty cool innovation. And there's a problem that Crisis Text Line faced as they started to scale this service, which was that there's a group of people called repeat texters. And repeat texters are people who text back time and time again that don't have a crisis. And it's just a few people, but they can take up to 40% of Crisis Text Line's capacity. So it's a real problem. And they said, well, how could we solve this? How do we deal with repeat texters? So we teamed them up with Noel Seo, a data scientist out of Pivotal Labs, with Bob Philbin here from Crisis Text Line. They said, you know, we could probably look at all of the data about repeat texters, every text they send, all the information about them, and write a machine system, some kind of algorithm that could read those in and automatically reroute who's a repeat texter and where they should go. And the end result of this, what this graph is trying to say, is that Crisis Text Line could then go from their old habit of waiting through 16 texts before they decided, a human said, oh, you know, this person's a repeat texter, send them to the website, to just 5 texts. And this was all actually done automated. So machines just listened to these texts and then eventually said, hey, you know what? These people are probably repeat texters. Let's put them somewhere else. And the end result is that crisis text line can now serve 20,000 more teens. And a nice cherry on top is that the surveys from these users have actually skyrocketed because the repeat texters themselves say, hey, thank goodness. I didn't want to go to a counselor anyway. I want to talk to somebody else. So actually a great sort of straightforward example of using algorithms to speed up a model that's already working pretty well. Another example that's not a DataKind one, but I think this audience might be a little more familiar with, is actually a fairly old example at this point around flu tracking. You know, the CDC and the WHO are always on the lookout for the next big flu outbreak. The way they do that is by stationing people at centers and hospitals and watching the kind of symptoms and make sure that we're not attacked by some huge superbug. But of course, it's a really time-intensive process. So a couple of scientists and data people said, how could we figure out where the flu is erupting sooner than using this process? And so they consulted some of the most sagacious minds of our generations, including people like the great Kim Kardashian. Yeah, think what you will of Kim. She's vocal on social media, including when she has the flu. So she, like many other people on Twitter and other networks, are constantly talking about when we have the flu or when we're feeling sick. And so from this, they were able to write an algorithm that pulls all those tweets down and actually is able to estimate with about the same accuracy as the CDC, and sometimes in cases about 2 weeks earlier, where the flu is actually occurring. And if you so they don't have to send anyone out. And if you put this on a map with where those tweets are happening, you get either a really cool or disgusting map, depending on how much of a germaphobe you are, of flu season in America. And so you'll watch as this goes to December. You'll start to see it start to erupt. It's so funny. This was in 2012 already. I felt embarrassed talking about this because it feels ancient in the life cycle of algorithm stuff. So what do we learn from these two examples, right? One thing to note is that this sick weather project is very similar to something Google did called flu trends. So instead of looking at tweets, they looked at what people were searching for. So if you search for, do I have the flu? I'm looking for, want to buy cough medicine. That was a signal to them. And I think there are two really salient takeaways from these examples, which really just scratch the surface of where algorithms are being used in health. There's so much in epigenetics and public health monitoring. But in just these two examples, I see two really important things. The first is that they use pretty novel data sets, right? So one was text messages coming in for every transaction. That's a new thing thanks to all the cell phones we have. This one was looking at passive data, like Twitter. And that's really a great opportunity for measurement because there are all these big passive data sets about what we're talking about, satellite imagery tracking what we do, that we can learn from. I think that's a really interesting avenue to go to if we build up our own analytic capacity to use it. The second thing I think it's important is that these still don't get at the problem of impact. They're both operational designs, right? They make something that works one way work faster or cheaper, or this one helps you get a reading on where the flu is a little sooner than the CDC. They're still not getting an impact. And so that's actually why I wanted to talk to this audience in particular about this, because we could just kind of stop here and go, okay, great, algorithms are cool, they make things faster, awesome. But we're seeing a lot of these algorithms being designed without a human-centered design process. And that means that they're often doomed to fail, or worse, do harm. So a lot of people, if you followed this story, know that the Google flu trends idea failed. And what they mean by failed is that the algorithm was really easily tricked. It worked really great when it came out. But then when people started searching for things like Bieber fever, all of a sudden alarm bells would go off, there's a huge flu across the nation. Right? So it's a simple mistake to make and a simple one to fix. The thing is, this was an algorithm designed within a tech company, not with the users in mind, and just kind of put out there. And that really, to us, got us thinking about these models of how we go about creating these algorithms when you're going to start bringing in data and tech people from one side, social organizations from another, the users out there somewhere. How do we think about design principles for building these kinds of systems? Because they're starting to show up everywhere and shaping our decisions. So one thing that we do at DataKind that I think is worth lifting the curtain on is we actually define these 6 components that we need for a good, successful project. It's very easy to think of us as data scientists for free, and a lot of people think, just jump the data person in, they'll fix it. But we found we really can't do our work unless we have 6 groups around the table. One is someone's got a very clear problem statement. Not I want to reduce poverty, but I want to reduce poverty by 30% in these districts in Detroit. That can be tough. The other are data sets. And these now no longer necessarily live in the organization you're serving, because they may not be surveys, they could be video from YouTube. So that's a whole other thing. Data scientists, of course, we bring. We bring funders to the table, not just for money, but because they have a view of the landscape of what's going on. And we also bring what we call subject matter experts, not just academics or people who know academically what's going on in the space, but also constituents, people on the ground. We recently did a project in foster care We not only had foundations working on that, but we brought in people from the foster care system. The kids could actually point at the data and go, hey, that's me. I'm that row. It's really important if you're going to think about how your algorithm is going to affect things. And then, of course, what we call social actors could be nonprofits, governments, whoever's going to implement this thing at the end of the day. And so at DataKind, our job has become not just to do data things, but to actually get all these folks together, talking to each other, translating between each other, and then building something that hopefully actually gets adopted and has impact. So as we've done this, we've seen 4 design principles that I want to talk about today. There are many more, but 4 that I'm interested in. 2 that I think, I believe, map to HCD, but 2 that I think are really fundamental to data and algorithms that I want to bring out to the community and sort of get some feedback on. The first is one I've heard from a lot of speakers on this stage, scoping. Finding problems can be harder than finding solutions. And I think our work is challenged by the fact that most people can't articulate their machine learning needs, understandably, but also that a lot of people conflate data with impact, not data as something that is a resource to be used in a project. So I'm often think of this time the Red Cross of Chicago came and said, hey, we've got this great data problem. I said, oh yeah, what is it? They said, we want to upgrade our database software, because then we can show our funders what we're doing from our database if we've got the new Windows version. And we were like, all right, well, okay, we could upgrade some software, but what are you trying to accomplish? I said, well, we've got all these fires going on in Chicago that are totally preventable. People just do things like put space heaters under blankets. It's awful. And we don't know how to stop it. We just kind of put brochures out there and we just say, hey, please don't do this. And so a data scientist talking with them said, well, that database you wanted us to upgrade actually has records of every single fire that's happened in Chicago. And we think we could get data from the government about building violations. We could put that together. We could probably predict where those fires are likely to happen. You could just go there. Right? That's a mind-blowing moment, right? Like, oh, wait a second. Well, if you can do that, well, what about this and then the other thing? So we really have to take a lot of time to step people back to the questions, as I think most people find in this design process. And we actually will do that either through just conversations on the phone or actually a work we started doing called a design day, where we bring everyone together and sort of think through ideas together. So just to say, that is just as prevalent here in dealing with data and tech as it is in the other spaces. And of course, doing this requires that we have a no jargon rule. And that goes beyond just making sure that no foundation says SDG and no technologist says API, because people don't know what those things are always. But it also means breaking down the barriers of intimidation. Because nothing makes people feel dumber than talking to them about math. And we've actually had projects go totally off the rails because everyone nodded along the whole way through and said, this is going great, everything's great. And then the whole thing was a failure, never got adopted. And when we asked the nonprofits what happened, they said, well, we kind of knew it was wrong, but we didn't want to say anything. We didn't think we knew, and they're the math people. So we actually do a lot of work to kind of make a safe space for everyone to feel like they're experts in their own work, but that everyone has expertise to contribute to this. So we do a number of other things that I think follow typical human-centered design, rapid iteration, et cetera. I think these are fairly similar. But the next 2 things we see, I think, are really specific to data and really need to be known, because I'm not exactly sure how to deal with them. The first one is that data is not fact, but a design process. It's the result of a design process. And this is huge, because so many people come and say, aha, if we have the data, we'll know. It's science, it's truth. These computers, they're unassailable. But of course, the second you take our phenomenological world in all of its complexity and all of its viscerality and boil it down to a quantitative value, you have made a myriad design decisions based on your technological limitations, what you've thought to measure or not measure, your own cultural and social biases. And so an example I think of all the time is work we did with the ACLU around stop and frisk in New York. This was the program where police were stopping and frisking people, and they're really curious on understanding if there's a racial bias in that. And so some people, some data scientists put this data through and they said, hey, we found something really cool. In one of these years, all of a sudden, they're like, no Hispanic arrests. That's crazy, totally drops off. And they start conjecturing about why that is. Maybe there are more Hispanic people in government. But it turns out, if you look at the race column, you may notice some letters in there you don't usually see in race rankings, like Q and Z. That's because the NYPD started adopting a distinction between black Hispanic and white Hispanic. Now, if you don't know about this design decision, you go ahead and you run your data, and Hispanic suddenly disappears one year, and if you don't pick it up, you just go, oh, I guess there's no Hispanic arrests. But in fact, you're missing a really crucial piece of a design decision someone made. And even aside from that, let's talk about the fact that it's someone's job to determine how many races there are. Right? This is a classic ethnographic and demographic problem when you do anything in kind of census or survey work. Who decides how many there are? And once you've decided that, how are the police, who are the ones entering this data, trained to recognize that? And even beyond that, if the police have a racial bias and you're encoding that in the data, and then you build algorithms that learn from that, how are you not encoding that racial bias in it? So, that's like a lot. That could be its own talk. But what I mean to say here is, a lot of times I think of data as being tacked on at the end. Great, let's just collect how we did and figure out what happened. But actually, we need to be thinking about this from the very beginning and really asking questions about who picked this up, why do we make the decisions we did, and really approach data collection and that choice itself as a design process. Now, that alone you'll learn if you take a statistics class. But here's the really new one, and just bear with me here. There's a question about how you know what your algorithm actually does. That's because we're entering an age where the people designing algorithms don't even understand how they work anymore. This one you could probably understand. This is called a decision tree. Decision trees are simple. They're yes, no's. This one will help you figure out if you should eat food you dropped on the floor. My decision tree only has one, yes. But the important thing is you know how I made my decision. If I ate it off the floor and I told you I came down this, you can go back and figure out how I did what I did. But increasingly, a lot of the developments in algorithms are coming from machines we don't understand anymore, like this complicated thing. This is what's called a deep neural network. If you've heard about deep learning, this is what we're talking about. It's a graphical representation of a super complicated brain-like thing that you just throw data at. I'm way oversimplifying. And it learns neurons that fire and bubble up into patterns until it can basically operate and do wonderful things like talk to you on a helpline when you're looking for help. A customer service automation. And so the thing that comes out of this is, this was a neural net that was trained on a bunch of images on the internet. And what people start to do once these things have been learned from the data is they go and they poke the nodes and they say, what do these things represent? And sometimes they make a lot of sense. That one down there is a diagonal line node. When you poke that one, oh, a face. That's really good at detecting faces. And of course, because this was trained on the internet, this one looks like a cat. Because that's all the internet is, cats. But what you don't see here is if you probe a lot of these, they just look like gibberish. And people go, well, what's that feature? Well, I don't really know. And there's a problem where we just kind of trust that these things work well, but they're not at all interpretable. And that might be fine if what this is doing is just tagging your friends on Facebook and it screws up. But what about when this is being used for sentencing in prisons? Would we prefer to use a model that works less well, gets lower rates of classification, but it's easier to understand how it's doing what it does? I would argue potentially. But it's a design decision that most technologists are not even thinking about, and they're just doing this stuff because it's the most performative. So that's why we need designers in this loop. Oh yeah, I was going to show you an example. And so the last thing to say is that even once these things are out in the wild, I'm always haunted by this Marshall McLuhan quote, because it's not just that we're creating products that people are going to use, we're creating decision-making machines that are going to have pretty unintended consequences on the things that we do. And so that could be as ham-fisted as the most blatant case of, well, we can build it so we should, which is a device or an algorithm that claims to identify criminals by their faces. This isn't to say, you've been arrested and we want to find you again. This is based on your facial structure, we think that you're a criminal. This is, yeah, a nervous laugh, right? This is like smacks of phrenology. And yet, this is what you can do, right? You can do it. The computer can do it, so shouldn't we do it? So that's a real design ethical question. But even more pernicious, I think, are the well-intended algorithms, like Microsoft's crime-ridden neighborhood avoidance algorithm. If I'm navigating through a new city, I don't really want to go to a crime-ridden neighborhood. I'd like if Google Maps or Microsoft doesn't route me through there. But what you may end up with here is wealthy people with cell phones avoiding poorer neighborhoods, creating a kind of digital segregation. Is that good? Is that bad? I don't know. You could make the call either way. But what I do know is that without human-centered design in the process from the start, we run the risk of technologists building things that kind of just serve the immediate needs without considerations of this whole broad social context. So I'm very glad to say that I'm not the only one talking about this. If you're interested in this topic, please check out Cathy O'Neill's Weapons of Math Destruction. Zainab Tufekci has an awesome TED Talk about this. And basically everything data in society does, they're just down the street. In fact, they have a conversation tomorrow at 4 if anyone's around about a pattern design language for how humans and AI can interact. There's a lot out there, and I almost want to pause here because I see so many phones up taking pictures, so please do, because it's a really rich topic. So I will end there by saying that this is kind of Wild West times. And we're getting out there and people are creating, this data revolution that we're in means that we can create these things more easily than before. And there's a great way that we could use them towards that poem of all being watched over by machines of love and grace. But we really, really need this to be a cross-cutting collaborative effort, because right now it's the technologists who are doing this. And as designers, or nonprofits, or foundation people, we need everyone around the table thinking about all these broader implications. I'm reminded of a quote I love, that you should take an interest in politics, because politics will definitely take an interest in you. So algorithms of data have already taken an interest in us. I think it's on us now to take an interest in them, make sure that they actually work in our interests. Thank you.